restart again. So with this video, it's a time-lapse video of some nice children cleaning the house. Not my kids. I wish my kids would do the same. Usually they do the opposite order. If you play this video the opposite order, that's exactly what they do. So, okay, the part of it, I like this when kids clean my house, but also I'm showing this video because for the point that we are in 2024, we have lots and lots of progress in computer vision, obviously, as we all know. So object detection, action recognition, whatever it is, just putting labels on actions or human pose estimation. So this is now all piece of cake, or more or less. And with most recent models like GPT-4o, so we also can get incredibly detailed descriptions of the scenes. As some of my previous speakers today already have shown that not just images, but also videos can be described very well. So it's actually just description of a single scene, but it has a very detailed, it's very detailed now. So, so this is all great. So now my point is that how does it help me to make a robot? So I gave hope on my kids. So how does it will give me the hope to make this room on the left to become the room on the right? Okay, so I imagine that I want to have a robot at home eventually, which will do some work for me. But all of this, so object detection, human pose estimation, scene description, so does it bring us any closer to the to this embodied understanding of the scene, which eventually should enable us to build robots which will do the job which we want? And this partly also, there was a question earlier today, how to evaluate the vision language models or the video QA data sets and so on. So to me, okay, I agree that just video and language, it has a right to exist. There are many interesting problems. So to me, the even more interesting problem is embodiment. So how can we learn embodied agents to do the job? And here evaluation becomes easy after you solve all the hard tasks. The evaluation actually becomes easy because you can evaluate, did the robot or agent achieve the goal or not? Okay, it's binary, more or less. So is the room clean or not? Okay, you can argue what is the clean room, but to me this is clean enough. So if I get this result, I'm happy with all what was in the pipeline. Now, okay, so let's look a bit at the GPT. GPT is amazing. So maybe GPT already does solve all of it. So here's an example of a messy kitchen, which, okay, assuming I have a robot at home, so a robot is asking GPT, what precise action should I do to pour milk in the from the purple container into the green bowl? Okay, so you see purple container somewhere in the bag, green bowl. Okay, so messy. So it's not so easy because you need to do something with the scene. Okay, so GPT comes up with a nice description, but it's a bit blind because all it says that, okay, locate the purple container, that's easy. Then clear obstacles, okay, maybe you can do it, but then pick up purple container, that's fine. But then green ball, how do you position green ball? That's already quite a bit of, so there is not much embodied understanding here. So like if I'm a robot, I should follow instructions. These instructions are not sufficient for me because I need to know what to do with this green ball, which has lots of other stuff. And okay, that's one example, and it gets worse. For example, here's a simple example of a bike, the specific bike, okay, without the top. So here, so where can you comfortably cycle with this bike? So it says lots of like streets. Okay, so it doesn't realize that there is a problem here. It doesn't realize that there is a problem with this bag, which is broken. So, all right. By the way, I'm not saying that. Actually, it was pretty hard to find this example, to tell you the truth. sometimes it does amazing job. So it's I'm wondering if should I be happy or unhappy, because on one side I should be happy because it brings me forward, but on the other side unhappy because it solves so much stuff already. But okay, so I still believe that embodiment, this is one part which GPT doesn't solve very much. And so this one example just tried in my hotel room yesterday. So here's a scene. Okay, GPT sees it, and okay, I described the scene, right? So now, what will happen if I move my hand up? What do you think? Okay, the contrast here is a bit. Yeah, so the GPT says that if you move your hand up in this situation, the pen will likely to lose its balance and fall over. Okay? Reasonable. So it doesn't know actually about physics, right? It doesn't see though that I actually pushed the pen in the hole. Right? One could realize it because actually the half of the pen or part of the pen is not visible. So okay, so here it is. So I'm asking GPT, surprise the pen is standing. So it says, yes, indeed, it's surprising. It can happen if you put it right. So all this is about that. Okay, vision is great. Lots of things happened recently. Well, we have to find our niche. Are we going to be out of jobs? So this is my niche. To look at more physics related and embodiment, because I think, and okay, so now to the question, so why is it not doing that great in these examples? My belief is well, it's natural that these models, they've been trained from lots of text, lots of images and videos, but there is a missing action there. So there is no like physical action in all this training data, and this is something what is fundamental if we want to train robots, and that's where I'm going with my talk. All right, so what are embodied agents? So this is some agents which should manipulate in the physical world, and they should be good in answering this type of questions. So what, like it's about planning basically. So if you want to clean a room, so you need to like plan on different levels. You need to first you need to know if you have a final state which you want to achieve. You want to know which actions should you do, and also once you plan, you maybe want to reflect: is my action is going to be a good one? And so, if I'm planning for action X, it's good if I'm also imagining and predicting what will happen to the world. So how do we learn all these questions? So to me, answering all these questions, so to me, the procedural data or instructional data is a great resource, which we are going to use. And okay, I'm not going to come up with a solution of the robot which does learn from the videos, but we are making small steps towards this direction. So that's what I'm going to talk about. Okay, so bear with me. Okay, instructional videos, you've seen them. Right. So here's some papers we've done over the few past years. Actually, first time we thought of using instructional videos was in 2010. I remember it was in ECCB in Greece, but then there was almost no instructional videos on the internet. So we had to wait until 16 when we did the first work. So today I'm going to talk about two more recent works. So with Tomasz, I think he's standing over there, which is about actions and state changes. So again, so states are fundamental, I think, from this slide. So if we want to change the world from A to B, okay, we need to understand what are the actions which lead to from A to B, and if I apply some action, what state I'm going to reach. Okay, so I'm going to talk about states and actions, which are very coupled, and two works. One is on recognizing this or discovering states and actions, and another one on generation. Right, so that's an example from Jean-Baptiste's work quite some time ago, 7 years. So basically, he was in this project, we were trying to discover given the initial states and what are the final states and the actions which connect them. So it was before neural network era. So now this work, which was CPR22, it was a bit more updated version of it and much more scaled. So the motivation is still the same. We want to understand the state and state modifying actions, and eventually to pass it to the robot. Nothing really big surprise. So we're going to lots of data, so how-to or similar instructional videos. So we filter them by some text, which comes with the narrations, because people narrate the videos, and people nicely talk about what they do and eventually also what they achieve. So getting this noisy data, so we can now try to learn a model with contrastive loss that will isolate the initial state, the final state, and the action which connects them. Okay, so there is a constraint. So it's very generally it's vaguely ill-posed problem, because you what cues do you have? You hope that initial states, final states in different videos should have similar semantics. Okay, should look similar. They should be in the right order, and that's basically all what you have. And so we are formulating this method by creating a few interesting constraints, which I'm not going to cover, that are in the paper. The challenges which one needs to the method needs to overcome automatically, because we don't have any annotation, is that the visual variability, so the things can look very differently. Long videos, we don't know where exactly in the video we have these state changing actions and next state, and also some videos which are not relevant. Right, and there are also the test data set for this task, which we created together with this work. And right, and that's the some results. Here I'm going to more skip through. So basically the method works, not 100% of course, but it does from a big, large corpus of videos, instructional videos. It can distill the two states and action which connects them. And this is quite general, so it can scale up to many different states and actions. All right, so that's was about discovering the states and actions. Sorry, this is too fast. So now more to this year work, which we presented CPR, is is now a trend of generating things. So we also try to generate states and actions, specifically because we already have this data set which I just described, which was automatically mined from YouTube videos, where we have pairs of states and they're connected by an action. So why don't we try to generate images? And this relates to why is it interesting at all? Well, generating images, why is it interesting? So again, for my purpose of embodiment, this is interesting for several reasons. One is that there actually work already now, which I call goal-conditioned policy learning, where you're given the current image, and if you have a state or the future image, so then the policy is learned to connect them, basically. And this also has relation to psychology, so what they call visualization. So visualization in psychology, or this cognitive science work, it's apparently that when we think of something, or when we want to, I don't know, have a great vacation, so you visualize and then you reach it. Okay, so that's what they call visualization. So it's similar to robotics, that you need to imagine first what do you want to achieve, and then you can get there. So that's the motivation for this work, basically. And of course, it's different. Okay, it would be otherwise too simple. We want to preserve the scene, right? Otherwise, if we just say that I want a cake, a frosted cake with a strawberry around the top. So if it's any cake, okay, Stable Diffusion does it. What we really want is this the second column. So again, how-to is our method. So you can see here that the table is preserved, the cake is preserved. So what's changed is the processing, whereas the two other methods don't do it. Similar here. So we want basically to keep the scene the same, but just change the state of the object. Right. So how do we do it? Okay, we take the previous method, which I just briefly described, we generate lots of data. And now, so if you ask why is there any, okay, so by the way, there were examples here in this slide where we go from one state to another state to the third state to fourth state. So how do we actually, is there any physics involved? How do we preserve the table? How do we preserve Avogadro? No, so there's no explicit physics involved, so it's learned. But because we are learning it from the instructional videos where the scene is preserved, obviously, because it's there is a physical consistency in the instructional video because it's real. So the method is learning to preserve the physical consistency. How we do it, also not very much innovative. So control net is a great method. Why not change it too much? So we are using it, but we are conditioning it with two things. So one is the text, so the action or the state, and also the initial image, because you want to pass the initial image and want to make sure that the image should not be, the scene should not be modified. Okay, so this is more or less it. So there are in control net and stable diffusion, there are nice parameters such as noise. So if you don't denoise, like these are denoising autoencoders. So if you don't denoise not apply much diffusion, then basically you don't change the image. If you apply too much diffusion, you will get on the right where there is lots of changes and you don't preserve the scene. So somewhere in between there is a sweet spot. All right, and so I guess how many minutes? Okay, well, so I should move on. So there's also question to evaluation. So in this paper, you might check with Tomasz later, but there's well, when the image generation is very hard to evaluate. So actually in this case, because we are generating something very specific, in this case, we actually come up with a quantitative evaluation. And I'm not going to talk about this. And there is also qualitative evaluation. Basically, which we compare, it's A/B testing, where we compare two methods and ask people, which method is better, and our method is better. Right, so some qualitative results. So here we go from from one state to another. Okay, so on the generated actions. So here on the very left, you see the transformation, just image blending, going from initial state to the action of warping a tortilla, and then the next video is the object state where tortilla is ready, and the same with the beer. All right, so I guess I should have a few more minutes because there was a delay. Okay. So I want to now put this work on a time scale and to argue about that we actually, we are talking about these instructional videos and steps and actions. So, but we are just looking at one particular spot on this time scale. So I would say this is around minutes. Okay. So this is where instructional videos and actions live. So that's where people describe like one step, another. So I would argue very shortly that there is another. We can go to the left and look at the second scale of seconds. And so here we will go from task planning to motion planning. Motion planning is also very important in robotics. For motion planning, unfortunately, people never talk in these videos. I'm moving my hands 5 centimeters to the left, right? So this is so we cannot actually use language here. However, so that if you have video demonstrations, like instructional videos, you can still use it. And so that's one work which I will spend just 2 minutes on describing, just getting the one idea. So here the demonstrations are a bit more curated. Okay, it's a DEX-YCB data set where the person just takes an object and moves it somewhere, right? So what people have done, us included, is that you can get some reasonably good reconstruction, 3D reconstruction of objects on the hands, right? So now you want to move this reconstruction to the robot, and in this case, the 5-finger hand, quite lots of degrees of freedom. And you just hope that it will work, and of course it doesn't. Okay, why? Because when you reconstruct, you don't have even very good reconstruction will not respect the physics. Right. So what we are doing in this work, we are taking these trajectories, but not as a ground truth, but as a guidance. Okay, so we train. So we are assuming now we move from image space to state space. We have control over everything. And we have these 3D trajectories which come from the video as a guidance, and train RL policy in the state space, which is much simpler now because we have these trajectories. Otherwise, like random search would take too long. All right, and now as we train this policy in the state space, then standard trick, we can now roll it out many ways, render it like synthetic images, videos, and then train now visual policy. And now what you see on the left here is the hand now, which is moving an object to a particular location, actually without access to the state space of the world, just from the virtual camera. Right. Okay, so I think I should be really working up. So now, okay, there is some. This is a problem of video playback. This is not a problem of the robot. Now I want to get back to my time scale and to argue that, okay, we looked at the seconds and minutes, but actually there is a long way to the right. So there is a hour scale, like event planning. How do I plan the birthday of my daughter? Days, vacations planning, and so on, right? And I would argue that actually there is not much. So we are talking about we are somewhere in the these procedural videos this workshop is about. We're somewhere in this minute scale, but to me, actually, there is not much difference here. Because at the end, okay, we are using these procedural videos to maybe learn how to kind of open an oyster. But then you also have books. You have okay, that's my timeline transposed. So actually, we do have text resources for all these timescales. So, for example, for cookbooks, manuals, IKEA manuals, travel guides, right? So more on the shorter timescales, but for the longer timescales, we have novels, we have documentaries, we have full history books. So this is, to me, more or less all the same. It just well, it learns something. It learns us something. It just learns it on a different time scale, and but at the end we need to make decisions, and that's what it is about. And so, okay, so these are text resources, but they're also image and video resources. And so we've been this workshop, we will be mostly talking about the upper part, the procedural videos, but they're also movies. And again, to me, the movies are also material which learns people how to behave in different situations, how to make decisions. So not much different from instructional videos. So why I'm talking about movies now? Because just today or a few days back, so we have a new data set out, which is called the SFD, it's a short film data set. All right. So it's a new movie data set. So it has many genres. It has a video QA, open-ended and closed. About 1,000 movies, about 5,000 questions. Now, again, here is a bit of difference for movies versus instructional videos versus egocentric. So Ego4D, of course, a great data set. So yet they're addressing with different things. So movies is really about storytelling, even short movies, as in this data set. So this, on average, these movies are about 13 minutes. Still, so they can have a very comprehensive story and involve many people and so on. So I need 1 or 2 more minutes and I'm done. So why do we need another video QA data set? Actually, there are quite a few reasons. So first, okay, we want to have a story level video understanding, and we want to have publicly available videos. So if you know that there've been movie data sets in the past, right? But they are not available for public because of obvious reasons of the copyrights. So this data set, so it's a short film data set. So it's a amateur experimental kind of movies, which is not commercial. So it is great. You can just go to YouTube and watch it or download it. And so the pixels are all for you. Now, there is another issue with the common movies. So if you want to address the story level video understanding, so where do you go? Movies is a great resource. But common movies, what are these curves? On the x-axis is the strength of LLMs. So you give to LLM the name of the movie and the question, okay? And it just answers it. And you see the curves going up. This is the stronger LLM is, the better it becomes. Basically, it knows everything about the movie already, but it's not the case with our data set. So the red curve down, probably because these are unknown movies. So okay, probably maybe LLM, maybe GPT has seen it, but it's just nobody talks about this too much on the internet, so it's not. So this is an important point. So there is no data leakage or data contamination, people talk, into the language models. Another interesting thing is that also quite different to recent data sets. So people talk about long-range video understanding, maybe in Echo 4D and so on. But how much is it really long range? So sometimes you might have a long video and you may have to search it, but then to answer the questions, you actually just need 1 frame. So here, what we are showing is that we are doing like taking one model, say Lobby, and we are giving it like short pieces of a video, like we break video into short pieces, and we are asking the question to each short piece. Scene level and movie level, just one. And then, okay, we see where does it answer better. And actually it does answer better on the movie level. It shows that many of the questions, not all, but many of the questions in this data set, they are really at story level movie scale. So you need to watch the whole movie to understand what's going on. Okay, another interesting aspect here. So we looked at just this transcript of the speech transcript, right? So people talk, and actually transcripts or speech has lots and lots of information in movies. If you just apply LLMs to this data, you get quite good results. And what you see here is that these results with recent models, they're similar to human performance, which is not the case for vision models. So to get the best vision models and the human performance, there's a huge gap. And this is good news for vision researchers that we are to, if you just want to, advance video understanding, this data set actually will be able to show you that, well, there is a margin, definitely. And also here we see that combining vision and language is actually good for humans. People do much better combining vision and language. In recent models actually do worse. So languages. So there are things to do here. So data set is online. Welcome to use it. I'm almost done. Summary. So embodiment is still a hard topic for vision language models, and then we should be looking at procedural videos at different time scales and try to make the best out of them for embodied agents. Okay. There will be votes in today's.
I think we're running a little bit behind schedule. We only have like 45 minutes for the post session. So let's figure again, and maybe if it stays like around for the panel session, yeah, some more discussion. Thank you.
see an example of the how to 1 million data set where you have clips with annotations obtained from ASR. So today I'll talk about two recent works for multimodal video understanding. First, dense video captioning, and then I'll show how to extend this work by using reasoning to improve the quality. And then in the third part of my talk, I'll show how these multimodal models can be used for vision language guided robotics. So what's the task of dense video captioning? The idea here is that we have a long video and we want to give for each of the events which occur in the video, we want to caption it and then also localize where in the video this event occurs. And the approach here is to have a joint approach which does jointly localization and text generation. The idea builds up on the peaks-to-seek model, which actually predicts the coordinates and then the labels. And so basically what we do is we produce one single target sequence, which consists of text and time tokens, which allows us at once to indicate localization and captioning. And to do so, we use large-scale pre-training from narrated ancient videos. So what we do is to take videos, we cut them in chunks based on the ASR sentence boundaries. We use this for large-scale pre-training, and then we can see on the left, bottom left, that then we can actually get these events localized with the captions in time. And here, more details on the model. So on the left, we can see that our image frames are encoded by a GLIP encoder. On top of this, we have a temporal encoder, which encodes the relation between the frames. Then, given that this is a multimodal model, we also want to encode here the text, which is obtained by ASR. And so here, what's important is that we not only feed in the captions, the ASR captions, but we also have the timestamps. Timestamps are encoded in a discrete way. Then we have this encoder architecture, we feed in a T5 decoder, and we can then output here in a sequence the temporal tokens and the corresponding captions one after the other. And so what's important here is to pre-train this model. Here it's pre-trained on 50 million YouTube narrated videos. We use the ASR sentence boundaries as event boundaries. And we have two losses, a generative loss, which actually uses the predictions of the ASR. So we use the ASR as a training loss. And then basically what's important here is that given that we want to train our model on video and text simultaneously, we use this denoising loss where we mask out parts of the visual input and the speech in order to be able to train the model on the speech also, right? Otherwise, it will just predict the ASR, which we have already given. And then if you compare the results of the state of the art, we can see that it outperforms the state of the art by a margin for dense video captioning. You can also see that it outperforms the state of the art for dense captioning, paragraph captioning, and it obtains results which are slightly better than the state of the art for video captioning. And then what's important here is that the training data is important, the training size data is important, but it's also important the quality also matters. So basically what we have done recently, we have used the LLMs as pseudo labels and to improve the quality, and we can then show if we improve the quality in this way, the quality of the overall model improves, and you can even push it almost up to just getting zero-shot performance. And then the time tokens help when we're training on untrimmed videos. And importantly, visual and speech information is complementary. So here in many of the data sets, state-of-the-art data sets, you can actually show that by speech alone, you get really already very good results. So using both together is important. And then the ablations also show that the denoising loss is important if we want to use speech during pre-training, and it's important to get a model which takes both modalities into account jointly. And then here, some qualitative results. On the top, you can see the speech transcribed by ASR into text. So this is the input speech. Then you can see the input frames. And then on the bottom, you can first see the ground truth and then the predictions by our model. And if you look at how it's chunked, you can see that the temporal localization is very good. And then if you look at the results of the captioning, you can actually see for the first example, cut the chicken is the ground truth, and then what's output by our model is trim off the coarse excess fat. And this actually shows that the model is actually giving a higher precision output than the ground truth. And this kind of shows that it's important to think about evaluation metrics for this problem. And then the second example for sports videos, so again, it kind of captions the videos very well. So this dense captioning works very well. And we obtain here, we have shown that we obtain excellent results for dense video captioning. There's still work to be done on the data sets, because the data sets are still not very long. So if you want to evaluate dense video captioning, we need better data sets, better metrics, and also like think about which detail of annotation we want. And then what are open issues? Small objects are not detected and described by the captions. So here we have work ongoing, which does object localization in parallel to the captioning and injects this and improves the captioning based on localized objects. Then rare events are often not detected. So this is why like a recurring problem of LLMs, that basically things which are not seen often during the training is not recognized during testing. And then basically one thing, so we'll show how to solve this in the next part of the presentation, is by using internal and external knowledge and have some reasoning tools to improve the performance of this problem cases. And so here we look at question answering with reasoning. So why question answering? Because it's actually easier to evaluate. And then just to understand what you want to do. So what happens after the cat jumps towards the end? And then basically here the cat misses the target about the closet and falls. So if we only see the first frame, we don't know what's going to happen. And so this kind of illustrates that basically what we want is we want to really model the temporal and causal relationships in long videos. And so basically for long videos, it's impossible, or at least very difficult, to process every frame. And the longer the videos are, the more difficult it is. And then if you look at this end-to-end foundational models, we have as input the question, the video, and we output an answer. And so actually these models perform very well, but A, they're not perfect, and B, they cannot be interpreted. So we don't know what's going on. So recently what people have done, they have proposed planning program generation. So they take as input a number of APIs, a number of different tools, and then use the LLM to generate the code. Okay. And then basically you have a code which you can then execute. You can call the different APIs and execute. And basically this allows you to interpret the results. But then basically the thing is that once you have generated the program, you cannot go back and get more details from the video. So you have this program which you obtain in one go. It's single step, but then once you have it, you cannot go back and improve the results. And so what we propose here is we want to go away from this one stage program, but we want to have a multi-stage model reasoning. So here the idea is really we have the same type of tools, but instead of just having one program, we want to have different ways of chaining them together. And this allows us to have this more modular reasoning approach and go back to failure cases. And so to start with, we implemented a simple baseline where basically we use just one API, which is a vision language model, which captions every frame. So just caption every frame. So we caption every frame. What's important, we also have not only the frame caption, but we also have the frame number. So we know where in the video this event is happening. So we have like the sequence of events which describes the video, and then we can feed this into an LLM together with the question and obtain the answer. So what this does is basically we have a very simple way of encoding the video, and then the LLM is used as a reasoner on top of these text inputs. And so basically what's surprising is that this actually outperforms GPT, which is a program-based approach. And here, for fair comparison, we use the same tools, right? So we don't have better tools here, it's the same tools. And obviously, if you have a better captioning and a better LLM, you can further improve the results, but that's not the point here. And then the next step is we want to further improve this. So by a number of different reasoning modules. So I'll go into detail for each of them. So the first one is event parsing. It's focused on the language. So what we want to understand is what are the events and relationships in the language. So for example, one example would be we having the question, what's happening in the beginning. So we know that we need to zoom in on the beginning of the video. We know that there's a cat in the video or whatever. And the question is, what is the cat doing? So we know that we have to invoke a cat, a tool for localizing the cat. And so that's done in the second stage, which is event grounding. So here we find the spatial temporal areas which we want to focus on for the question. And then this also allows us to be more efficient because you can really focus and zoom in onto the part of the video where the event is happening. And we can also see how different events in the video chain together. And then the last part is the event reasoning. So here we look at what the objects which we have detected. We can ask additional questions on them, generate the questions, and then also caption each frame, combine this together and predict the final answer. Okay, and so basically this multi-stage decomposition leads to more focused generalizable programs. And basically later stages are informed by the prior stages due to vision and language. And so here you see the examples of a few data sets which we use for our evaluation. We have two types of answers, either multiple choice or open-ended. The two last data sets, in particular, ego schema was designed to be longer range video understanding. So here we have a longer context which comes into play. And then if you look at the results, so here the first line is random. In case of multiple choice, it's 20% because we have 5 possible answers, 0 if it's open-ended. The next row shows if you use an LLM only. So if you just use the ASR here for answering the questions, we can see that for next QA and ego schema, the results are already very good just by using the language information. And then the row below shows the results from the paper ViperGPT. And then the row even below is ViperGPT Plus, where we upgraded the tools which were used in ViperGPT Plus to make it exactly comparable to our approach. And so then we can see that by just using this very simple frame captioning baseline, CFE, we can see that we get an improvement in the performance. It's actually surprisingly strong for such a simple baseline. It's actually a very good baseline. It shows that a very simple tool already gives good results. And then we can see that by using our more VQA approach, we get a further improvement, which is consistent across all the data sets. And then basically the improvement is nice, but you could say having all these tools and all this effort, why is it only the improvement that much smaller? The one thing you have to take into account that it's more efficient. So we use 5 times fewer calls than if you would call like the full grounding approach. And then the other thing, which is why the improvement is not higher, is that the data sets are quite limited. So in many cases, the answers are not very good. And basically, so if you look at the failure cases, often it's actually something where you don't really know why this data was put together like this. So it's really important that we get better data sets. And the second thing, which is missing here, is it's only a single multi-stage but single chain model. So basically, we don't have backtracking. And so this is something which is very important that you also have backtracking. We have shown recently by adding backtracking, you can further improve the performance. So these two things are to be kept in mind. And then also, if you look at the different ablations, what's working, what isn't working, you can see that all the 3 stages help to improve the performance. So they're all important. And then here, comparison to the state of the art, you can see that it outperforms zero-shot performance for all compared to all the state of the art methods. And then if you look at the top rows, you can see that it's on par or better than math models which have been fine-tuned on the training set. So here we don't use the training set at all. And let's look at an example. So why is the cat lying on its back at the end of the video? So first, we show results for JCEF. You can see here, the prediction is tired, while the correct one would be ground truth. And so basically, the cat is doing other things in the video, and it kind of summarizes the information incorrectly together. If you look what this visual programming does, ViperGPT Plus, again, it outputs tired, so it doesn't really know what's happening at the end. It doesn't focus the evaluation on the end of the video. And then lastly, if you look at our model, first you process the question, you know that you're looking for a cat at the end of the video, so you can really go to the end of the video, detect the cat, and then ask specific questions about what the cat is doing, and you can then see that the cat is actually playing at the end of the video. So you can see here what is the cat doing? It's playing. Who's playing with the cat? A person. So it's getting petted. So you can have all these different replies. You can really examine what the cat is doing, summarize this together, and get the correct output. We can also use this in addition to when you ask a question to not only answer the question, but to also localize in the video where this question is answered. And you can see here, we obtain significant improvement over the state of the art because our method is really tailored to localizing the events in the video. So we have shown that this simple but efficient baseline gives good results. We have introduced more VQA for multi-stage model reasoning, and we have validated it across a range of different video data sets. And so what are the open questions for the research? So we need better long-range data sets. This is something we really need urgently in video understanding. So we're currently working on setting up such data sets, which are well-defined, longer range, and cannot be answered by text. So we want something where we really need the visual information to understand what's going on, to do this research on video understanding. And then another thing which we're currently looking in is how to connect and localize events, localize elements in the video. So basically, you want to understand the story, you really need to see how different elements in the video connect together. And to do so, one approach is to localize events or objects spatial temporally. And then basically, we also want to see how we can further improve this reasoning tool use by adding to answer more complex questions. And then maybe last point, the prompt engineering remains fragile. So either we manage to improve it or we maybe set up models which can be adapted to this reasoning capacities. Okay, and then in the last part of my talk, I'll show how we can actually use these multimodal models, which we have set up for taking as input vision and language now to guide robotics. So here the idea is what you want to do is we have an instruction to tell a robot, go to the fridge and get a drink. And so the robot should understand the language, be able to model the visual environment. So it sees the visual environment as a stream, as a video stream. And then obviously it also needs to plan and execute the task. And so the first approach which we designed was for this synthetic environments, for it's synthetic houses where the instructions are go to the bathroom in the bedroom with orange stripes, make sure the faucet is not leaking. So here we show that if you have a fully transformer-based model, which takes as input the text, the history encoded as images, and then the observations also encoded as images, we can then encode this as a multimodal, cross-modal transformer, cross-modal and transformer, and then just predict the action. So we can really see here, we can basically leverage what we have seen for video understanding and then train it in a way that we can also predict the action. And then if you look at what's necessary, so these multimodal models, obviously they work well, but if you're in an unseen environment, it's not sufficient because you kind of need to know more how to navigate around an environment. And so for navigation, one thing which we found important is to also model the environment. And so here what we have is we have a very simple implicit map, which models, like which has a grid structure to kind of find to localize the different parts of the scene. And you see here that the cube represents symmetrically the scene, and then on the right, you can see actually the layout of the map. So inside the cube, you kind of see where you are, you say where you have been, and that allows you to determine where to go next. So we update our transformer structure with these new observations. And how does this look in detail? So what we have initialized our map with zeros. We just say we don't know what we have seen, where we are. And then over time, so we encode our image, put it into multimodal transformer, which takes as input the image and the instruction, the text, the language text, and then we feed in the implicit map, update the implicit map, and output the action. So we can do this iteratively, and at each step of our navigation, we update our map and put out the instruction. This actually shows that we can increment our transformer architecture, our multimodal transformer, with this map, and we can actually pre-train it and use the same information and learn basically how to generalize from these vision language models and add this map. Then it's important to have a few auxiliary losses. So here we have visual feature prediction, explicit map construction, and also semantic features. And then once we have this, we can show it in virtual environments. And then once you have it in virtual environments, we can train it on a few examples in the real world and really then navigate around the real world. So here the category would be go to the plant, here go to the sofa, and we can really then execute this in the real world of the robot. And then one thing in addition to the maps, which is really important for if you want to interact with the visual world, is to have 3D information. So basically, if you want to go somewhere, if you want to grasp an object, it's really important to model things in 3D. And so here, what we have added to our multimodal model, we have added a 3D point cloud representation. So we take several cameras, we merge the point clouds. We can also improve them based on some object models. Then we feed them again in a multimodal transformer, and out comes basically in 3D the position of the robot plus the position of the gripper. So we have here the 3D information, and so basically it's important to have 3D because if you want to grasp an object, you need to know exactly where it's in 3D. And the same for navigation, you also need to know where it's in 3D. And then basically there are different ways of augmenting the images with 3D information. Either you have depth or you reconstruct it, but in any case, it's very important here. I think this is also something which is interesting. There's not enough data here. So basically, there's also some research going on how to increment the data, how to get more data for this problem. And then here an example, put the white plate on the target. So here the robot grasps the white plate and puts it on the target. So here the idea is really, how can we generalize to more actions, like basically grasp the red plate, the blue plate, and so forth, and like really learn things which we haven't seen before from our pre-training data, which is multimodal, and then learn from this data. Basically, ideally, we just pre-train it, learn a few actions, and then be able to really learn how to interact with the world. Okay, and so basically we have seen that current approaches result in excellent results for video understanding and robotics. Obviously, there's still things to be done. In particular, we have to do high-level planning and reasoning. And for vision, there are more to be explainable. And for robotics, because there you want to go away from simple instructions and have more complex instructions, then I think it's more important to make the models even more robust and explainable so that you really see and can explain if they're failure cases. And then finally, something I'm also interested in is to design next generation visual models by interacting with the real world. So basically, if you interact with the real world, you can really localize when you have a failure case and use this as direct feedback to improve your visual models. Okay, and before concluding, we have a couple of job openings. We have internships, we have a PhD fellowship, and some research scientist positions. So if you're interested, send me an email. Thank you for your attention.
We have about 5 minutes for questions. Please use the microphone.
Baseline the JCEL approach. So I mentioned every frame is captioned.
Yeah.
So I was wondering, I mean, videos are probably duplicate frames or frames that captions will be the same. How do you, I guess, somewhere basically?
Yeah, but here it's just a simple baseline, right? So here I don't know, it's not every frame, it's every fifth or whatever, it can be every 10th frame. But I guess we also have some work going on which removes the redundancy, right? But here is like really this very simple baseline is that you just take the frames and LLM uses the information to understand what's going on, right? So we would have the duplication, and the goal is not to remove the duplication or to make it easier. It's just like the LLM summarizes, and it actually gives good results. If you just feed in all this frame information, you summarize it, it gives actually good results for summarization. And so removing information would be more if you want to be more efficient, right? Then you operate directly at the frame level to remove redundant information.
Thank you.
Hi, thank you so much for the very nice talk. In your talk this morning, and maybe in this talk also, you touched on the limitations of current long video data sets. So if you are focused on generating new data, which aspects would you focus more on? Like generating actions which, or like focus on actions which needs long context, or even generating like longer videos, like data sets with longer videos than what's currently out there.
Yeah, I think basically, obviously, you want to have longer. I mean, obviously, just if it's just longer, that doesn't mean anything, right? There needs to be some content in there, but I guess, and then I think one thing is to try to generate it automatically or at least semi-automatically. So I think this is something which is interesting, and then like check for failure cases, right? That you see it's difficult. So either, I mean, you don't want to say it's an action or not an action, but you want to have some kind of measure, like for example, run this simple baseline, see if it works. You can see it's like easy and you can discard this, right? Another thing we're doing is if ASR already gives you good results, we just discard it. So these are the things I think you want to look at, not so much getting into this definition of being an action, not being an action. It's more like seeing what's difficult, what are the failure cases, and then kind of get stuff which is difficult to do, right? Because you want a data set where people can improve upon. You have enough failure cases and it's not perfect, by the way.
Thank you.
We have time for one question. Anyone?
So I saw that in your baseline just to caption every frame, basically that is the image model, right? And other work which is more VQA, which is about using tools to solve these videos. But at the same time, there are also many, at least now there are more and more like video language models. So like so what do you think what are the cases like where the video large models might be like better than those image LLM, which just caption like everything, and also how that compared to the third paradigm, which is agent based approach. So that's my question. Basically, we have image LLM, video LLM, and we also have this agent based framework. Then yeah, what do you think of these three?
Yeah, I think so. Basically, maybe the last part, the agent based, it's just like, I mean, basically that's what we're having is like not the agents, but it's like just one set of agents, right? And if you had agents, they would go backtrack again. And this is what I said is kind of missing, right? That you don't call the tools only in one order, but that you can kind of backtrack, right? So you go forward, you call the tools and then you execute. So you have this whole chain. But then basically, if you have an agent, I mean, whatever agents are called, but then you would probably say, at least our agent-based work, we go backtrack. And then if the answer is not correct, then you can see if you can find something better, right? Which makes it a bit more complicated because you need to have some verification, you need to access some external, in general, you need to have some external information to validate where you are to do this backtracking correctly. So I think this is just the first step, and we're currently looking at how to, I mean, call it agent or call it backtracking or call it iterative improvement, right? So you can do it like once you have the secret, that's an iterative improvement. And then the other thing with respect to, I don't know, this frame versus video, this is actually a good question, right? Because basically, if you have videos, you kind of also give in the frames. Like, so what do you gain by looking at these frames jointly? And so you do have some temporal information, obviously, but if you have the frame numbers, you also feed it into an. So I was surprised actually how well this works, right? So frankly speaking, I was thinking you need to have this video-based models where you feed in all the frames because otherwise you lose too much information. But basically here, given that you have the information and then you feed it to an LLM, you still have this temporal structure which is there, right? So the question, I think it's a good question. What actually do you lose by not looking at the frames simultaneously, right? Because you do have the order still given, but the fact that if you look at frames simultaneously is missing, right? This is the only thing which you're missing here. So if you have like a motion, like somebody is running and walking, maybe here you would have the confusion, right? And that could be, I mean, one workaround could be that you look at chunks of video, right? So instead of captioning every frame, you caption a couple of frames, and then you would have this information about the tempo. The short tempo motion would be given, right? And then I guess the question is, if you want to capture this very longer information, I guess just pulling out these types of information is probably good enough. And you kind of reduce the complexity by a large margin, right? To break down the complexity because you're not looking at all the information at the same time. But I guess it's an open question. This morning I was thinking maybe having some mid-level information would be actually interesting to not have to go all the way through and feed out in all the context. Of course, you could argue, other people would argue that if you feed in all the context token to make the context longer and longer, and then you have solved the problem. So I think it's kind of an open research question.
Thank you so much.
Let's figure out again.
So now we'll continue with our second speaker of the second session. We're very glad to have Juho Kim with us, who's an associate professor at GUIS, and he's an expert in human-computer and human AI interaction, because one of the most important aspects of procedural videos is teaching people how to perform tasks. Welcome.
Thank you. Yeah, this is my first CVPR, and I'm really excited to be here. But procedural videos are dear to me since I've been working on these types of videos ever since my PhD, which is more than 10 years ago now. And mostly as an HCI researcher, I've been building interfaces and interaction techniques for helping people better work with these videos. So today I want to talk about some of the work that I've been doing in this kind of domain, and hopefully bring in some of the fresh perspectives in looking into how we look at these videos as research materials. And you won't be hearing much about like model architectures and benchmarks and model performance in my talk, but rather I want to focus more on how people use these kinds of videos for their everyday tasks. So you might be wondering, like, what kind of research do you do then, right? So I would say my research is mostly driven by the goal of helping people in their actual tasks of learning and searching and navigating these videos. And also I'm informed by how people interact with these videos, looking at the video interaction logs and how to leverage that to help people better use those videos. And often interaction is really the unit that I focus on building and understanding, and using that to really guide the rest of the research process. And then when it comes to actually building the techniques and systems, I use more model and data-centric approaches, and it's an iterative cycle. So this whole notion of taking more interaction-centric approach to building AI systems was something that I gave as a keynote at NeurIPS in 22. So if you are interested in this kind of topic, I recommend you to watch this video. Today will be a shorter version, focused more on procedural videos. And today I want to talk about 4 threads of research that I've been doing in this space. And it'll be like a whirlwind tour of these different projects, spending just 1-2 minutes each. So the goal here is to really get you the conceptual nuggets behind these ideas. And like as a computer vision AI researcher, you might be wondering, like, why should I even pay attention to this kind of research? And my answer is to really build bridges. I'm here to start talking about collaborations and build bridges in maybe formulating research questions in a way that has broader real world impacts, or design tasks and benchmarks that are closely aligned with how people actually use these videos, rather than just being contained in the benchmark world. So that's the context. So first, I want to talk about this idea that I call learner sourcing, which also happens to be the title of my PhD thesis. So there are all these how-to videos, instructional videos that embed procedural knowledge. And of course, we know that finding information, repeating certain steps, or skipping certain aspects could be difficult for those videos. And a lot of work in computer vision and also HCI community have focused on maybe summarizing videos or presenting this hierarchical representation of the task could be beneficial for people. But instead of fully automating this generation of summary, we took a different approach. We built this interactive platform where learners who are learning through these videos come in, and they are given these questions once in a while as they are watching the video. They answer the question by describing what's happening in the video. So as you can imagine, this is sort of an organic way of collecting video summary labels from people who are actually watching the videos. And then underneath the system, what's happening is this multi-stage workflow that aggregates these responses from people, computationally, coming up with high-quality summary labels, so that this summary can be obtained through the collaboration of organic learners and AI. And similarly, we've been expanding this idea to generating concept maps for a video. So if we have something like this concept map,
lecture content.
I'll this for a while. Once you have this kind of concept map that's generated, it could be used as a navigation guide for learners and also serve as a summary for the video. And of course, we do that with learner sourcing, where learners who are watching the video are providing certain bits of information that could then be used by the system to generate high quality concept maps. So you might be wondering, what's the benefit of all this? And I would say if we were to take a more model-centric approach, we would be solving the problem of automated summary generation or concept map generation techniques. But in those systems that you've seen, our idea was to really think of it as a co-learning system where humans and AI are learning at the same time, while giving people pedagogically meaningful tasks for them to perform. And the artifact of what they do, like summary labels or concept map labels and links that are used by machine learning models to further learn on their end as well. So machine and AI are learning at the same time. And I would argue that putting like human learning as one of the objectives for these systems can have great benefits on humans who are using these videos. Moving on to the second thread, I want to talk a little bit about multimodal, but not in the sense of multimodal models, but multimodal approaches to watching and authoring these videos. And a lot of videos that people here are working on are things like cooking videos or furniture assembly, things like that. And a lot of these tasks require manipulating physical objects. And if we watch people using these videos in the real world, they don't really have the bandwidth to do the fine-grained navigation of videos using their hands. So voice navigation could be useful in this context. And we know existing video interfaces support navigation, things like skip 5 minutes, go back 30 seconds, fast forward. But when it comes to content-based navigation, existing support is fairly limited. So we built this interface. So this was work done in like 2020, 21. So the technical stack might not be quite up to date. But one interesting aspect that I want to highlight is that we often make the assumption that people want to talk to their video player. That was really not the case. Not many people actually want to have a conversation with their videos. People just want to give it the commands, give it the keywords that they're interested in, and they're kind of hoping it would kind of bring them to the frame that they want to. So that kind of gives a clue as to what are the problems that are worth solving if we are to put this kind of system to people in the real world. So what we ended up doing was to build this system where it allows people to say play, and it would play the video, and also more keyword-based navigation. You can say sugar, and it shows the parts of the video that have things to do with sugar.
Show next.
And you can add and remove like stacking these keywords. Now you can see
Butter.
sugar and butter, they're mixed together, and it kind of locates frames that have likely frames that contain useful information. So there's more like NLP and computer vision pipeline behind this, but focus here is to really direct your attention on it may not be the like dense captioning or the detailed Q&A that might matter to people. It might be just stacking of keywords that could actually help people. And in a user study, we were able to demonstrate that in terms of temporal, cognitive load and effort that goes into navigating the video, frustration that people have, this way of navigating video significantly improves these dimensions. And in thinking about like which domain we should focus on in tackling these kinds of questions about procedural videos, we looked into objects and actions, like how diverse types of objects are existing inside the videos, how many actions are existing in the videos. And based on that, we had this kind of map, which kind of helped us decide which domain to pick. And often when doing research, picking the right domain is an important task. So hopefully something like this could also be helpful for people who are about to decide which domain to pick for their next project. Another project that I want to focus on is on the authoring side of things. Authoring instructional videos can be quite tedious. So we came up with this system for using natural language and sketch, hence multimodal, right? So you can sketch the part of the video that you want something to be edited, and you can use natural language to describe your editing intent. Like whenever a display appears, add a slow zoom in towards the display. So what the system then does is to interpret the temporal dimension based on the understanding of a user's natural language intent, and also look at find the spatial location of where it should happen, then turn that into actual editing operations and actually make the edits. So here's the editing interface, authoring interface that we built. Like on the right-hand side, the user can describe what they want in natural language. Like here, and they can add the sketch to describe where they want this to happen. So this is a multimodal aspect of it. And then these summary of edits and the parsed results of here's how the system interpreted the user's intent to be, and user can make further edits and turn on and off different edits that the user has issued so far. So user can navigate different kinds of edits that have been made so far, and decide to add them, not add them, compare them, and so on. So in terms of the pipeline, we're using different kinds of off-the-shelf and existing open source libraries to do offline kind of pre-processing of the video so that it's ready to accept different kinds of user intents. And in online, it does a temporal, spatial, and edit interpretation, again, based on LLM and libraries like Click. So that was about multimodal editing of the videos. Okay, moving on to the third research thread. Here I want to talk about having lots of different videos and lots of different users. So the context here is, let's say we have 500 videos on how to make chocolate chip cookies, or let's say we have 1,000 users watching the same video. Are there meaningful like user traces or meaningful patterns that could be gained from multiple videos in this context? So in this work, what we tried to do was, let's say multiple people worked on the same task of doing a 3D modeling of a chair. That we might be able to identify a few meaningful patterns in how people approach this task, right? So it's as if we can identify these branches or different approaches to doing this task that naturally emerges as people do the task. And in a real like a mock-up design kind of task, this is sort of the task graph that we were able to generate based on people's actual demonstration. In a similar vein, we had some work in the context of surgical videos. Surgical videos are also procedural in nature, right? Often in a longer time span of multiple hours. But then navigating and comparing these videos is something that a lot of surgeons and residents want to do, but have very poor support from existing systems. So what we did was to automatically segment the videos in terms of the meaningful steps that are happening inside the video and cluster them based on their temporal progression. And what this allows us to do is then offer filtering and searching and navigation of videos in different ways. And something like this might also be possible where multiple videos could be played at the same time in sync for that particular step. So for example, as you can see in this video, if the user clicks on this particular step, then you see all these videos that are at that step. So you can have kind of visual comparison, comparing. Sorry, the video might be a little bit difficult to watch for some people, so pass over quickly. So once people are given this kind of interface to navigate the video, we were seeing certain benefits in terms of actual learning. So we ran this study across 9 hospitals in the US, 41 residents, and we compared their learning performance, human learning performance, against the baseline video interface that's like YouTube. And we were able to observe learning benefits in terms of answer correctness, coverage, and quality when people were given this kind of video interface based on segmentation of the steps that are happening in the video. And another project that I want to talk about in this context is what if we can leverage large-scale user interaction log traces. So this was done by my PhD student, Serin, who's actually sitting right there. So here our idea was, let's say, here's this software tutorial of, how to do this Photoshop task. And we might actually have thousands of people watching this video. And there are meaningful signals that could be gained by looking at how people use this video. So for example, people can, sometimes people skip certain parts of the video, rewatch certain parts of the video, or watch steps in a very specific sequence that's somewhat different from what's actually in the video. So we can leverage these signals to maybe understand how difficult a step is. So for doing this, we came up with 6 different measures that have something to do with estimating the difficulty of a step, looking at execution time, repetition time, and back jump, how frequent that happens, and how frequent the pauses happen inside a video, and miss rate and refollow rate. So based on that, the interface then can inform people as to here are the things that you might want to watch out for when performing this particular step. Or when certain thresholds are met, it could even report as to, are you stuck right now? Do you need some help? Right. And another kind of pattern that we tried to identify was step relevancy or dependencies between different steps. So by looking at how people actually navigate different steps, we might be able to identify, from where to where people navigate inside the video. By having an understanding of the individual steps inside a video, plus the navigation patterns, we can give support like, 59% of the users watched it more carefully. Many people decided to replay this step or slow down here. So it's drawing people's attention so that they can be more prepared. So here are the examples of using multiple videos and also leveraging interface traces. Okay, moving on to the final thread, I want to talk about sort of what I think is a grand challenge or really an open challenge moving on. So here I haven't done really a lot of work quite yet, but I think it's personally very exciting. So I want to present as sort of like current and ongoing and future research, which is tacit knowledge. So tacit knowledge, as you know, is knowledge that's hard to be explained, verbalized, and externalized, right? So often it's we kind of know it through practice and exercise and experience and mastery, but these are not really in any kind of data sets, which makes it difficult for agents to really have this knowledge embedded when they perform those tasks, which makes those performances rather unnatural and missing certain bits. And I think this is analogous to what Yejin Choi refers to as dark matter of intelligence and language. So her comment is more about common sense kind of missing in a lot of what we do with generative AI and LLMs. But when it comes to procedural tasks, I think it's the tacit knowledge that's really like the dark matter. Dark matter in the sense that, dark matter in the sense that it's something that's not really visible, not really captured as data, but something that actually has a profound impact on how people perform tasks. So to better understand what kind of tacit knowledge even exists, we had this recent paper on trying to characterize different types of tacit knowledge that are existing in graphic design as a particular domain of choice. So here what we did was to do a literature survey to understand what kinds of tacit knowledge even exist. And we came up with 4 high-level categories that occur when people try to possess a new skill, express some knowledge, acquire new skills, and manifest them. And there are those individual categories as well. And then we also collected 123 actual instances of experts describing something that's tacit and tried to categorize them into elements, action, and purpose. So in this example, you can see increasing readability by adjusting the attributes of the font. Here we have the purpose of increasing readability. Adjusting is the action taken, and attributes of the font is the element going into this tacit knowledge instance. So far, we've been doing more of categorization, taxonomization of this work, but I think this is going to be useful building block in kind of deciding what kind of knowledge is even worth capturing and turning into data sets and benchmarks moving on. And in a similar vein, again, Sabin's work right here, we looked at what kinds of information types even exist in these instructional and procedural videos. And through, again, what we call, thematic and open coding of data, which is a qualitative research methods, analyzing these instances from videos, we came up with 8 high-level categories and 21 action types that are happening in those videos. So what this allows us to do is to be able to do some kind of n-gram analysis on these videos in terms of what kind of information types are presented when in the video, how frequent, and based on that, we can adaptively decide what kind of information type to be appended to the video when we do the video generation, for instance. So again, this is more of a building block kind of work. And in today's workshop, Sabin again presented sort of a next step of this direction of work. So a lot of work in the vision community has focused on fine-grained like action labeling and using LLMs to provide high-level or more dense captioning and so on. And in this work, we want to continue this line of work in thinking beyond capturing what's happening inside the video in terms of action. We want to get fine-grained labels on how it's being done by coming up with this kind of elicitation method, like human labeling kind of method that helps people, that asks people certain questions about tool usage and how exactly that's happening. But starting with this, our bigger vision is to really expand to things like why is this step happening inside a video, to get at the reasoning side of it and collecting that as valuable data, but also things like hidden context and hidden dependencies and tacit knowledge. And being able to collect that and building data sets and benchmarks, I think would be a great contribution, really unlocking the best possibilities of tacit knowledge. And I want to end with this slide. This is a recent book published by a good friend and colleague of mine, Matt Bean. The title is The Skill Code. Like a lot of people here, I think, care about skills, like videos that contain how people learn and master skills, videos that embed this kind of knowledge. And he's an organizational ethnographic researcher who studies a lot of people in doing these procedural tasks. And some of the interesting findings are that he notices that it's really the apprenticeship, learning over shoulder, that happens a lot in those cases rather than through formal education. So a lot of this bond between the human novice and expert matters a lot. But then with the introduction of new technologies, like let's say robotic surgeries in the surgical rooms and operating rooms, can sometimes break this bond, right? The productivity goes up, the quality of surgery goes up, but the problem is residents are not welcome inside operating rooms anymore, so they kind of get kicked out for like economical reasons and efficiency reasons and so on. So interestingly, surgical outcomes go up, but juniors lose their opportunities to learn. So they kind of rely on what's called shadow learning, indirect ways of learning. It points out that challenge, complexity, and connection are the basic components of how we master skills. So like having this kind of understanding hopefully can give you more insights into how people master skills, and hope that can help you better formulate the research questions in this kind of domain moving on. So just to wrap up, I presented 4 interaction-centric research threads that I've been working on over the past decade or so. And I think there are interesting challenges that come out of these threads. In the first system, where I presented the idea of human AI co-learning systems, I think we could really present it as a joint optimization problem, right? So a lot of recent agent-driven work focuses on humans teaching agents, agents teaching humans, and vice versa. Then like how might human and AI learn at the same time? Like joint learning could be an interesting objective function to aim for. In terms of multimodal, I think determining the right combination of which modality to use when, especially understanding how people use different modalities for different tasks and purposes, I think is a really interesting and important question. When it comes to modeling multiple demonstrations, multiple users. I think an interesting question is how might we effectively represent this aggregate task knowledge, 500 chocolate chip cookie recipes? What's a good representation to really capture the meta performance of particular task? And finally, when it comes to tacit knowledge, it's really just beginning. And I think we need better ways to elicit, detect, and infer tacit knowledge in the procedure and build automated agents or supportive agents that help people in those tasks. So that's all I have. Thank you for listening.
We have time for maybe 2 questions.
You.
Thanks for your talk. So at some point, I guess you mentioned about questions you ask viewers to then be able to annotate the videos. Can you, I guess, give examples of the types of questions you asked them? You made sure, like, if you did any kind of quality work on it, to look at answers were actual grounding in the video.
Right. So in the summarization system, the question that we asked was, could you describe what was happening in this video for the past minute or so? And we asked this question each minute inside the video. So that's one example of it. And you know, summarizing the content of video can be a meaningful activity for learners. So that's one example. In another system, we also had a case of self-explanation, like seeing the explanation of a task. We asked people to rate how helpful the explanation was, and then try to come up with their own explanation that could be better than what they saw. Again, that's a useful kind of learning activity, and at the same time, system gathers a new explanation label that they could use.
So if I understood correctly, the validation of which one of the explanations was, or the caption was also based on feedback from other people.
Right, that case, yeah. And we also had some like automated checks to see, but that's not quite enough as signals. So we often rely on the social signals of other people rating how helpful the material was. And we had this like reinforcement learning agent that kind of tries to learn the rating so that adaptively it presents more high quality explanations to more people.
And then the setup that you were working on this, like, I mean, you referenced learners. So can you talk a little bit more about the setup? Was it in a school setup or?
Yeah. In different systems, we had different sort of deployment setups, but mostly I've been working with adult learners in a more informal learning setups, not in like classrooms, but people who are just aspirational designers learning to do Photoshop, and they would kind of voluntarily engage in this kind of efforts. Yeah.
Okay, let's end this video.
Okay. Okay.
Our final speaker is Dima Daman. She's one of the pioneers in egocentric video understanding. She's been working a lot on this topic, a lot of papers on action and object.
It's working on it.
No. Unmute. And yes, a lot of very interesting work coming out of her lab. She's a professor in Bristol, by the way, and also in DeepMind, like lately. Yeah. And yeah, we've seen data sets like Epic Kitchens, also like very great work in Ego X4D. So ready? Yeah.
I hope so, yes. Thank you for persisting, especially those with jet lags like me.
hopefully we can get through the remaining 30 minutes. And we will be talking about procedural videos, and there are no LLMs in this talk. So, okay, so the title is Procedural Videos from the Fine to the Course. And basically, there is huge success now in learning from procedural videos, perception. Amazing data sets. We've been hearing about that from the people created the data sets and the tasks. Huge interest and success in learning graph-based representations, tracking the progress of procedures, as well as lots of tasks related to monitoring errors and assisting users. I believe in the past couple of years, we made huge progress in all these aspects. So what's next? What do we need to do to proceed further? And I will argue we need three things. One, we need finer grained understanding of these procedural videos. We need better appreciation of context in these procedural videos. And finally, a bit of global understanding of what these videos obtain. And hopefully, I'll show some insights that we found in these. And I'll start with fine-grained understanding and a bit of early work we've done. Basically, Hazel has led on trying to understand skill, and very much a follow-up from the previous keynote on the need to understand skill in procedural videos. And in this work, we were looking at stuff as simple as people drawing and asking humans to label which of these two people is exhibiting a higher level of skill. And it's really very, very hard to put this into language. People will absolutely agree the person on the right is exhibiting a higher level of skill in this task. But if you ask them to explain why they think this is the case in language, they will give you very different points of view, right? They might say, oh, the strokes are better, or the expression of the face. They kind of pick on very different things, and that showcases that it's not a linguistic thing that they see. They do see a visual signal that gives them a perception of skill. So in this early work, we gave basically an I3D model that was looking throughout the video, two videos. So this is, pairwise understanding ranking, and trained the model to predict that indeed, based on some supervision, one video is exhibiting a higher level of skill than the other. And indeed, just doing that, you get good numbers. But if you start asking the model to figure out what made it pick up this or that, you'll see that it's picking more of a bias in the data as opposed to, what really is exhibiting skill. We had to add some level of temporal attention modules. I think at that time, people weren't even calling it attention, just about temporal attention modules, and say, now you need to tell me two things. I will give you two attention modules, and one should attend to what's good in the videos, and that's through a loss. So you really need to give to tell me what do you like, what is increasing your skill score, and another attention score to tell you what is weak, like what makes you down score. And through this rank aware loss, we made these two temporal attention modules specialize. And looking at the outcome, you learn a lot about skill understanding. For example, this is what the network had picked up across a variety of tasks as evidence of low skill. For example, in the makeup, it's people removing a bit of makeup. This was picked up automatically through this loss. In the origami, it's people unfolding. This is evidence of low skill. And then when it comes to high skill, it's interesting to realize that what you learn from the data is different to what you think. For example, hesitation, so pausing to think, is evidence of high skill in drawing, but evidence of low skill in putting makeup. And all of these things are things that tell us a lot that skill is really underexplored. And despite the fact that this work is now 5 years ago, I still think this is something we should look more into. A follow-up from this work, also by Hazel in collaboration with Ivan, was looking at adverbs. So trying to look at procedural videos and trying to understand whether we can distinguish the way in which an action takes place by looking at the description, particularly the adverb associated with the verb. So in this work called action modifiers, we would take the video, the corresponding description, parse it to recognize the action and the associated adverb. We call the adverb a modifier inspired by prior work focusing on adjectives and objects. Then we really don't know which part of the video exactly exhibits the rolling quickly. So this was weakly supervised. We would take some, a word embedding. So this is word to vec, and we would embed the verb. So this is where the verb rolling is, but we assume that there is a modification to this location that moves it from being a general rolling to a rolling quickly. And that modification should generalize across different verbs. So the objective here is to try to embed this video close to the modified version of the verb roll to become rolling quickly, and to jointly learn this embedding as well as this modification in this case. And some bits of this are now outdated, but the concept still stands, which is focus on the word rolling, find where it is in the video, then now learn an embedding that makes it rolling quickly, assuming that indeed this is the case. And this was able to recognize and spatially locate where mixing is happening. So that's the thick border around the video. So the thicker it is, the more confident we are it's mixing, then passing it into, okay, what type of adverb it is, and recognizing this indeed is mixing quickly. And then you can see, a different video with a different verb. So this is, in this case, mixing, and indeed you're still recognizing it, but in this case, the mixing is happening slowly, and trying to generalize across verbs. Of course, there aren't enough examples at the moment to kind of make this very general. I still think focusing on both the pairwise understanding of skill or the descriptive understanding is very, very much underexplored. Recently, along with a huge consortium, and if you want to know more about this work, I encourage you to attend either the oral on Friday or the poster session. We've been looking at skilled activities through the form of EgoExo videos. But the coolest thing about this dataset, in my opinion, everybody likes bits of pieces about their work, is how we created a 3-level understanding. One is from an expert, call it the teacher. So these are people who are trained to mark experts in this domain. So they are, they're people who are ranking dancing, and they're providing a score, but also a free form description with sketches saying the person here isn't putting their hand clearly. This is someone trained to teach basketball player and says the foot position here could be improved. And this type of data is extremely rich and shockingly detailed. We still don't know much how to do with it, but it's a very, very huge, rich resource. Interestingly, we have another layer of understanding of procedural activities here, and it's called narrate and act, where the person is describing what they do. This person could be a novice or not yet a teacher or an expert, and they're saying, I do this because I think it should be done like this. And the contrast between the two is very interesting, right? Then there's the third layer, which is the atomic descriptors. These are the narrations you're used to if you've used EPIC or Ego4D before, but these two additional layers are fairly new and are underexplored. The last bit on the finding, I'm not going to talk about this because Ivan kindly presented very nicely the Gen how-to. Just in case you were not here earlier, make sure you pick on this on the Wednesday poster session. So the first thing is fine-grained is very much underexplored. Let's look beyond fine-grained and more into a bit of context, and I'll present a couple of works here. The first is work we put recently out called Every Shot Counts, and this is an attempt to count repetitions in videos. While this is not in procedural videos, again, I think procedural videos have a lot of counting that we should explore, and we're not looking into this. So in this work, I'll start with a few examples. What you can see is the video. You'll see the ground truth with the labeled repetitions, as well as the predictions at the bottom. The sum of these predictions, the sum of this density map is a prediction you can see, and this is applied for a number of typically sports videos. These are the CountX, the rep count data sets. But really very interesting as a task. And how do we do that? We do that through trying to find basically context, things within the video that are very similar. The videos here are variable length. So basically we chunk them into clips, but what you see here is a variable length long context. Then you have, during training, these exemplars, one or more, that you try to attend to. However, inspired by prior work in object counting, we also learn a 0-shot latent variable during learning. So during inference, we don't need any exemplars. During training, you either have some exemplars you attend to, or you also train this zero shot. What is this zero shot doing? It's actually trying to attend to the self-attention outcome of this video to say, okay, what's the signal here that I need to attend to? And through this cross-attention layer, set of layers, you kind of predict the density map. The sum of it is the count in this particular video. This approach works really well on all the data sets, outperforming quite easily. You know, sometimes you do some work and you really need to tweak a lot to outperform. This wasn't the case. This was like, you know, you do it and it does really work on a number of data sets. It also can generalize during inference. So you can say, count this, and it's able to kind of take that. You cannot have that and have zero shot counting, but you also can say, can you count this specific exemplars? And you know, what you see, the counting tasks tend to be the typical metric is off by 1 and off by 0, but the metric doesn't really say how off by you are, right? If you're off by 1, then, and what you can see here is a visualization that this model not only gets these off by 1s right, but really it's much closer across the diagonal than prior approaches, basically inviting better metrics. But yeah, you can see the diversity of exemplars here. And this generalizes across data sets and to what we call open sets, so actions that are not present during training. Credit to Saptarshi and Alex who've led this work. If you look at the work, you can look at a nice visualization of how well this performs across length of videos, length of repetitions, number of repetitions, and their presence within the data. The other bit on context I want to talk about is a work from the last ACCV, so a couple of years ago. And this is very much these procedural videos, and it really questions the two types of retrieval tasks we've had until today, which is video paragraph retrieval, where you see the full video and a full description of this video, versus clip sentence, which is you see one clip and its corresponding sentence. Here we are looking at the context of this clip, i.e. the local context of this clip, and see whether that improves clip retrieval. Maybe this becomes more obvious when we look at the examples. So the top example is pick the onion container. Now, this is the bit where you're picking the container, but you have absolutely no idea what it contains. So if you purely look at this, you will not be able to know what container you're picking. So the evidence that it indeed contains onion comes a bit later in the video, but not a lot later. So this is not like hours later, but there is some evidence around. This is another one that says, add water to the washed quinoa. Now, this video itself doesn't have any evidence that this quinoa is washed, but the previous clip does. So these are some of the results, and then I'll tell you a little bit about the method. So indeed, if you only look at this, which is divide the dough in half, the rank in retrieval might not be high. If you actually start looking at a bit of context, then what you see at the bottom is the amount of attention that the model is choosing to look into the context. Really, the ranking improves with time across a diversity of data sets. So you see UCook2, you also see ActivityNet, and you see some of what triggered our interest, which is Epic Kitchens, where really some of the captions tend to be very difficult to pick if you don't look at nearby context. Nearby context is very important as we go into longer videos. We cannot do video paragraph retrieval in data sets as long as Epic Kitchens or real procedural long data sets, because it's really meaningless. It's the nearby context that matters. So how does this work? And I know, things have improved over time, but the trick still, I think, is a critical thing to look into. And I would be very happy to talk to others whether they agree on the importance of neighboring context in video understanding rather than overall context. So this is a video, and you're seeing 3 neighboring clips. You can encode these, and you can add a relative positional embedding to the clip you're interested in. So if you're interested in the green clip, then this gets a positional embedding of 0, and the one before it is a positional embedding of -1, and the one after it is +1, right? You can pass this to a transformer that then learns an attention, so learns the green one, but empowered by its nearby context. Now, if I want to represent the yellow clip, I will then feed those clips again, but here my positional embeddings, my relative positional embeddings are different. So clip yellow is the 0, clip green is -1, and clip blue here is the +1, is the relative context. And here we're embedding these contextual things, and we are training the contrastive learning to say this one, even though it had seen green, it should see it as context. So it should be very far from the textual description of the green clip. I hope this is a little bit clear, and if not, ask me after or refer to this work, which is now public, and the code is. Another aspect of context that we've been looking into is audio-visual context. And this is work to be presented this Thursday called TIM. So you have here as input a long visual audio context, and you want to understand what's happening in the video. Until now, we've been seeing aspects of this where LLMs are being fed with what is happening between minute 2 and minute 3. Here, we want to really ask the same types of questions, but without an LLM. We want to elevate time intervals beyond their current status. So we want to take the start and end time of a particular event triggered by an understanding of its modality. So we want to say, what is happening between this time and this time, particularly if you focus on the visual modality. We put both the start, the end time, and the modality into an MLP, basically encoding the time interval. This is a little bit different to the type of approach currently transformers take, where positional embeddings is single points in time, right? So you put position embedding 1, 2, 3, 4, 5. This is an embedding of an interval. What's happening between 1 and 4? And the outcome would be what's happening in this visual signal. You can do that even with multiple modalities to say, now what's happening between this and that time, but let's focus on the auditory signal. And if you're aware of epic kitchens, then you know we have these two types of annotations, epic kitchens and epic sounds. So we've been training with those two signals. That means we have one transformer without an LLM that we can ask it questions like what's happening between minutes 3 and 5 in the visual domain, between 0 and 5 in the auditory domain. So we are feeding these time intervals through this query MLP. Right. There are not many tricks beyond, except the fact that this time interval MLP is the key one. We're using it for our queries, but we're also using it for our features, because features are not really momentary stuff. They tend to be, especially if you're extracting audio or video level features, they are representing a particular extent. They could be half a second, 1 second, they could be 2 seconds. Why not represent each feature by its time interval? So we feed these time intervals also through the same time interval MLP, giving each feature this representation of its extent as well as its modality. What comes on top is a vanilla transformer, and the outcome is how do we like whether it's what's happening in the visual or the auditory stream. The nice thing about TIM is that we outperform approaches trained with a lot more data than us. We only use public data, so this is very different to prior approaches that have performed really well. We've outperformed them without having to use the same amount of private data. This was also tested on the perception test, which is another dataset from Google DeepMind that includes both video and audio signals. If you're interested, come to talk to Jacob and Jason, who are in this room. Also, they can show you how we managed to look at the TSNEs of these time intervals, and over different datasets, we show that the network learns the 3 dimensions of an interval. It trains the duration. So it actually is encoding durations distinctly. Where is the start of the interval and where is the end of the interval across the 3 axes, which we kindly align here nicely so that you can see the point. So this is to be presented on Thursday. Before we conclude, how much time do I have? 5 minutes. I'll go quickly. I'll talk to global understanding of videos. So videos have been like this partial view of the world. And recently, I am very excited about taking them beyond this partial view into the real representation in the world. So we've done this epic fields where we've taken our videos and now we have estimated camera pose. So videos exist in the world. And recently, we put this paper out called Out of Sight, Out of Mind, where we are actually tracking the objects that appear in the camera view, but we're now tracking them in the 3D world. What you see here is the 3D view of the camera, but there are no dynamic objects here. So this is static, right? The dynamic objects will appear in the ego view and will appear as dots here because we're tracking them as dots, excluding their size, but you can see the objects actually moving in the environment. We don't know what object the person will be using. We don't give them any semantics. We just say something here is moving, and we see that the person leaving this thing, I don't know what we should call it, the pot of the rice cooker, they're leaving it in the sink. As you look away, the model is capable of figuring out that this thing is now still in the sink. This is very important for procedural videos because humans have a good spatial understanding of the world. I'm going to skip the method. Please look at the paper for details. What's relevant to the procedural bit is that we are able to know whether an object is in view or out of view because we are tracking all objects in their world space. We're able to know if an object is in view but occluded. It could be inside a cupboard. You're looking there, but you can't see it, or behind another object. And we know whether the object is within reach but not in view, which again would tell you where you imagine you are performing a process. We know whether these objects are within your reach or you have actually put them away. Very quickly, where I think things should go next. On the fine-grained aspect, I think a lot more research is needed on fine-grained understanding. I think local context is a lot more important than long context. And I know there is this race for long context. I think local context probably solves most of it, especially when it comes to procedural videos and is underexplored, especially in the domain of full video versus clip. And finally, I think a video is a partial observation of an actual world. I'm very keen to estimate a 4D representation of space if needed. And if you're interested, I'll be happy to get any ideas you have. I always get the pleasure to get invites and talk about work, but this is the hard work of a large team who inspire me every day. And I'm very grateful for their very, very hard and dedicated, careful work. Thank you very much.
Let's maybe do two questions while we set up the panel.
And otherwise, we will have some questions to start with, and let's see. So one question is, what is missing in the current procedural video datasets? And if we are about to get a new procedural dataset, what would you do? Yeah, that's a question. If anyone wants to get started.
Yeah, as I already tried to make the case, I think tacit knowledge, knowledge that's often not externalized, verbalized, texturized, and even visual, I think is a key missing piece that I think could be turned into a very valuable text.
Maybe relate how much do we need procedural videos nowadays with the lots of knowledge inside the LLMs. I think there is an additional value in that, but I would critically check what is it actually, and then this would be the answer to the question.
So I think there are two reasons we as humans go online to seek procedural videos. One, because we actually don't know how to do something, right? I have no clue, like I look at something broken at home and I have no clue how to do it. And once I kind of figure out the trick, I do have the skill set. So the procedural video is just giving me like this, oh yeah, it's from here, right? And this is like a one moment, I just look at it and I know how to do. Then there is the other type of procedural videos where I know how to do the task, but I might want to be better at it, right? I do know how to something, but maybe I am seeking additional skill level, or I'm seeking to improve, or someone like a perfect chef knows how to dice perfectly. I can still cut my stuff for my salad, but I'm looking for an additional skill improvement. And I would like, some sort of a distinction that helps us identify which of the two are we seeking, or a data set that allows us to figure out, is this a skill that once, or a step that once I see it, I'm done? Or is this something that needs potential improvement? Some of them might be like, you might continue learning forever and you will not reach perfection. And that distinction to me is missing from current datasets.
Yeah, probably seconding that a bit, and probably also answering with a question here, what might be missing, and I'm careful, might be kind of like a common task that we can all kind of like share and work on as kind of like an umbrella for all those different aspects that we have seen today.
Yes, so I think I totally agree with what Ivan said, especially on the LLM side. So now we know that this model, they know a lot about very standard procedures. So we need to make sure that we also collect like procedural data that are very like out of domain, meaning that if you think, for instance, about a video about how to make pancake, like most of the LLM, they will know the main step. And so if a model is able to recognize very quickly from a few frames that you have a video of how to make a pancake, I mean, it will derive very quickly the procedure without even having to look at the other frames. So we need to also make sure that we have very exotic or very weird procedure that no LLM can do without having seen the frames, like really all the frames.
Yeah, and maybe also ask the question if you really want to single out procedural videos as a special case, right? Because basically there's a lot of boundaries. And, I mean, it was a long time ago, it was without or whatever. It was very justified that we wanted procedural videos, but today it would be just like you play a ball or you play a game, and it's not a procedural video per se, but it's also interaction with objects, right? So I was actually wondering if it still makes sense to have this as a special case of understanding.
Yeah, just adding one last bit, I think the complexity of tasks is something that we can see more variety of in those data sets. I think existing data sets tend to focus on somewhat simple and well-defined and clear tasks, which have their own benefits. But I think moving on, covering more complex real-world scale tasks might be something we want to see more of. And there are many cases where procedural and declarative knowledge are kind of mixed in a single kind of task as well. I think these hybrid or mixed type of task might also be interesting to investigate. And on that note, recently we've started some collaboration with OpenAI in understanding these complex tasks, like examples being like building an interactive dashboard on the web, or writing a marketing plan for a company. So these are tasks that require multiple types of knowledge, a mix of procedural and declarative knowledge with a lot of dependencies between different submodules. And I think we are kind of moving forward to more complex and multifaceted types of tasks.
Thank you all for all your amazing talks today. I feel like I actually learned a lot from each of you, so I just wanted to say thanks. My question is about, I think there are a lot of types of things that we can visually see in videos that are not very common on YouTube. So one of the examples that came up today were, for example, surgical videos. We might not have like so many examples on YouTube of all these different types of surgical videos, especially like more niche type of things. There's a lot of maybe different applications that are really not super present there, but maybe things like large language models might actually have some internal knowledge about the way that these procedures are done, for example. Or so I guess I'm curious what you all think the role for maybe formalizing the notion of the procedures could play for these type of scenarios where we may not have a lot of data available visually, but we do have a language model that knows the steps, for example, or I'm just more curious if you have any general thoughts about these type of videos that are maybe not so common on YouTube and what good approaches could be there.
Yeah, what kind of examples have the surgical videos in mind, or?
Yeah, I mean, I work on a lot of healthcare applications, and in particular, they're not like super common on YouTube. So that's where I'm coming from with this question. So I thought the surgical example was great. I work on a data set where it's a lot of videos inside hospital rooms, and those are not very common on YouTube either. So there are a lot of these sort of domains where, you know, for privacy reasons or other reasons, you can't have these data just like on the internet.